zeros. So in the next step, we basically have to determine how exactly we're going to solve this integral. To solve this integral, we first must substitute. Let's suppose that x is equal to 2 multiplied by r divided by r naught. So if we rearrange this equation and solve for r, we see that r is equal to r naught multiplied by x divided by 2. Now if we take this and we take the derivative of the left and the right side, we get the following result, where the left side we take the derivative with respect to x and get dx, and the right side we take the derivative with respect to r and we get 2 dr divided by r naught. So next, if we rearrange this and solve for dr, we get that dr is equal to r naught multiplied by dx divided by 2. So basically, the entire point of this step is so that we can substitute and simplify this equation to make it more simple so that we can actually solve it. So notice, we can take this dr term and replace it with this quantity, and we can plug in this entire term into this r. So we replace r in terms of x, and we replace dr in terms of dx. And that's exactly what we do in this step. So also notice that we have to change the boundaries. So the lower boundary remains at 0, but the upper boundary must change. So notice the upper boundary is the point r naught. So if we plug in r naught into the r, we have 2 multiplied by r naught divided by r naught. The r naughts will cancel and x is equal to 2. So the upper boundary in terms of x is equal to 2. So the area is equal to the integral from 0 to 2 of 4 multiplied by r squared, where r is this quantity. So r naught x divided by 2 squared divided by r naught cubed multiplied by e to the power of negative. Well, this entire quantity, 2r divided by r naught, is replaced with x. So we have e to the negative x multiplied by dr, where dr is replaced with this. So r naught dx divided by 2. So notice that this 4 will cancel, and also notice that our r naught cubed will also cancel, and we are left with the following result. So we bring our constant outside of the integral, and the area is equal to 1/2 of the integral from 0 to 2 of x squared multiplied by e to the negative x multiplied by dx. So we basically simplified our integral from this to this. Now in the third step, we have to actually integrate by parts. So we apply the concept of integration by parts that we use in calculus. So that basically means we have to replace our x with u and our v with x as well. So basically, we take the integral of u dv and equate that to uv minus the integral of v du. So let's move on to this quantity. So if we look at the following result, we can basically say or equate that u is equal to x squared and dv. So u is equal to x squared and dv is equal to e to the negative x dx. So we set u is equal to x squared and dv is equal to e to the negative x dx. So if we actually take a derivative of the left and right side of this equation and this equation, of this side and this side, we get du is equal to 2x dx. And if we integrate both sides of our dv and this, we get v is equal to negative e to the negative x. And this quantity simply disappears. So now we know what u is, we know what v is, and we know what du is. So we are ready to actually integrate by parts. And we get the following result. So all we do is basically notice that we have this 1/2 on the outside of the integral, and this entire quantity becomes u which is simply this quantity plus this entire result. And we evaluate from 0 to 2. So notice we are not done in terms of integration by parts. We have to apply integration by parts a second time. So to basically solve this, we have to set u equal to 2x, and we have to set dv equal to e to negative x dx. So, in the fourth step, we apply integration by parts another time. So, let u is equal to 2x, and du becomes 2 multiplied by dx. Now, dv is equal to e to the negative x dx, and if we evaluate the integral of both sides, we see that v is equal to negative e to the negative x. So, if we apply the same exact process to this step, we get the following result. So 1/2, we have the bracket negative x squared e to the negative x, which comes from this quantity, and then we apply integration by parts to this, where this is u and this is dv, and we get the following result. Now, if we actually evaluate this integral and we bring out the constants, we get the following result. So 1/2 multiplied by e to the negative x multiplied by negative x squared minus 2x minus 2, and we evaluate from 0 to 2, we get about 0.323, or equivalently 32.3%. So the probability of finding our electron within the spherical region of the Bohr radius R0, which is equal to 5.29 times 10 to the negative 11 meters, is given by 32.3%. Let's suppose that we are asked to use the radial probability distribution to calculate the most probable location